This is problem 14-11. A small block B rotates with the horizontal turntable A in the figure below. The distance between the block and the axis of rotation is r equal to 3 inches. The angular acceleration of the turntable is alpha equal to 5 radians per second squared, which is equal to a constant. And the initial angular velocity is 0. Determine the time t1 when the normal and tangential components of the acceleration of the block are equal. The number of revolutions n of the turntable between t equal to 0 and t equal to t1, and the angular velocity of the turntable at t equal to t1. Okay, so there's a bunch of information here that we need to look at in order to feel like we understand what this problem is asking us for. So some things that I want to point out are we have a distance between the block and the axis of rotation, which is this distance r here. It's basically the radius from the center of the turntable to where the middle of the block is located. Okay, the angular acceleration is the acceleration of the rotation of the turntable, which is also the acceleration of the block if the block isn't sliding, which we need to find out if something like that is the case. Okay, and the initial angular velocity. So angular velocity is this symbol, the omega. All right. So keep in mind that the alpha looks kind of like an A, but the A is a linear acceleration. Okay, and then for velocity, linear velocity is v, and then angular velocity is omega. So, and it's not w, it's omega. That's what I'll be calling it. So don't mix up that when I'm saying omega, I actually mean that little w-like symbol. All right, and we can see that the units are radians per second squared. Okay, and the rate of acceleration is unchanging, so they're highlighting constant. Okay, but the initial angular velocity is 0, so you could go ahead when we're doing the problem, you can say omega is 0. So they then talk about time t, and they say that the time t1 when the normal and tangential components of the acceleration of the block are equal. Okay, so they're saying that the acceleration of the block in the tangential direction, which is the direction of motion at that instantaneous moment, and the normal acceleration. If the block is moving in a circular path, then there is an acceleration towards the center. All right. And so they say at time t1, the normal and tangential accelerations are equal to each other. Okay, that must be useful for something. Okay, and then they talk about t being equal to 0 and t being equal to t1, which is basically our final time. And so they want the angular velocity, omega, at time t1. All right, so that is a breakdown of the problem. And don't forget, the number of revolutions. So we're going to find out how many times this turntable has turned during this time from 0 to t1. Okay, so let's take a look at the math of this problem. So let's review some of our given information, like r equal to 3 inches, alpha equal to 5 radians per second squared. Okay, our initial angular velocity is 0, and that's also has units, and those units are radians per second. And then they want us to, well, there's a t, initial t of 0, and then a final t. So you kind of say initial t and final t of t1 that they care about. So they want us to find the normal is equal to the tangential acceleration, all right, at t equal to t1. That's something that's given. And they want us to find, so they want us to find that time, right? And then the number of revolutions, and then the angular velocity at time equal to t1. Oh, sorry, velocity, not acceleration. All right, so how will we approach this? Well, We can get the angular velocity and the angular position the same way we can get the linear velocity and the linear position in previous problems. So just as we would be given an acceleration of some value, then we integrate and we can get the velocity equal to some value plus c1, and then we can get some position, maybe r or x, okay, or s, whatever it is that they happen to be giving us in the problem, and then plus c2. Okay, which remember C1 is initial velocity and C2 would be initial position. All right, but in this case, we're going to be taking the angular acceleration, integrating to get the angular velocity, and then integrating to get the angular position. So that's same situation mathematically, but instead of linear motions, now it's rotational motions of acceleration, velocity, and position. So if we integrate alpha, which is 5 radians per second squared, then omega is going to equal 5t plus 0 for the c, okay? Because we were told that the initial angular velocity is 0. All right, and then if we integrate again, we will get angular position, which is going to be 5 over 2t squared, okay, plus c2. Now our angular position can just be where we start, so 0 again. Okay, so we have our angular acceleration, angular velocity, and angular position. So now we have talked about in the chapter that the linear acceleration is equal to alpha times the radius, the angular acceleration times the radius length, radial length. And the normal acceleration is equal to the angular velocity squared times the radial distance. Okay, well, are these values that we know? Yes, we know alpha. So let me move these guys out of the way. We know that alpha is 5 and the radial distance is 3. So therefore, the tangential acceleration is 15. Okay, and then the angular, the linear normal acceleration, omega t, is going to be 5t, sorry, not omega, well, yeah, omega t, I guess I could say that, but omega is 5t, and then we'll square, and then the radial distance is 3. So we'll end up with 75t squared. All right, now the problem wants us to find what value t is, or t1, or they say t1 is when the tangential acceleration and the normal acceleration are equal. So therefore, if we set 15 equal to 75t squared and solve for t, we end up with t equal to 0.447 seconds. Okay, so then we can find values that they ask for at time t1. So for part B, they want us to find the number of revolutions from time 0 to time t1. We know when t1 is right here. We just found it. So we need to know where the turntable is positioned angularly, meaning how far it has turned at that time. Well, we have a position function that is a function of time. So we can find that theta value by plugging t1 into t. So 5 over 2 times 0.447 squared. That equals 0.5 radians. It's actually 0.49952, but yeah, I'm going to just round up. I mean, I'm not going to take out a whole bunch of digits, okay? Now, 0.5 radians is technically answering the question, but by the way, it was also 0.796 of 1 revolution. Okay, so you can do the radians conversion to figure out how many revolutions there are. See if you can figure that out. Okay, you can ask me for clarification if you need it. But 0.5 radians does technically answer the question. All right, And then they want the angular velocity of the turntable at time t1. Well, we have a function for that. So angular velocity is equal to 5t. And then we just plug in our value for t1. So 5 times 0.447 seconds. Right? That ends up equaling 2.24 radians per second. And that answers the question.